Wow, thank you so much, Skylar. I'm just sort of gobsmacked. I'm just sitting here going, that's amazing. Mostly, I've got a load of brilliant questions from our audience, which I'll put to you in a second. But just for my own curiosity, when am I going to be able to buy a smart jumper? Because I'm always too hot and too cold, and that just would solve a lot of my problems.
Yeah, it's a good question. Nothing's on the market today. And, there are many companies that have tried to work on smart materials, all of the best, the Nikes and the Adidas and the, New Balance and, any of those, especially in the sports domain, have tried to make smarter materials. And often you'll either get something where it works, but you don't even know it works, or it's a marketing gimmick. And there really isn't something that we've shown similar to what we've shown where it both is dynamic in the physical performance and behavior, but you also can see it and feel it. It changes the design, it changes the behavior of it. And we're really interested in how this like quote unquote smartness becomes new agency for the clothing. So anyway, the short answer is there's nothing on the market yet that does that. There's lots of things that'll say like, nanoparticle fiber, something here that makes you cooler. And you're like, I can't really tell, but sounds good. But I do think that the field is shifting towards that. And, that's why we collaborated with the Ministry of Supply and we're collaborating with other brands in order to try to translate it out of the lab, into these processes. And everything that we've done is using the same exact industrial technologies, the industrial knitting machine technologies that they make full scale, full production shoes, clothing, garments. So in our mind, it's very, very scalable, but yeah, hopefully soon, not yet.
Yeah, and also presumably the problem is also not just the fact that you can have it and it works, but I can put it in the washing machine once a week. I can, wear it, tear, what I mean? That it has to have some kind of longevity because it's all right, it works in the lab in a test, but 3 months later after walking around, heating it up, cooling it down,
Yeah, totally. And, we've done lots and lots of tests and there's many, many more. And that's why we often partner with these industries because they know how to go. Like we're very good at going from impossible to possible. They're very good at going like possible to scalable. You know what I mean? And there's a big gap there. Oftentimes, although the things we're doing are fairly complex, they're kind of the low hanging fruit, like things that this would be amazing, but it's not possible today. Let's figure out how to make it. And then we collaborate with a lot of industrial collaborators in order to try to go the last mile, which is, frankly, often much more difficult. And there's many more people that are good at doing that. But yeah, testing regimes, washing and drying and durability testing is all part of that. Yeah.
All right. Well, I better crack on with some of the audience questions. Otherwise, people will get upset. So many really good questions. They're all kind of just all over the place. I'm just going to kind of throw things at you if that's okay.
Yeah, sure.
One of the points which came up was this idea of a circular economy. So Matthew McGuire asked the question, what are the opportunities to use this wonderful technology to make a circular economy a reality? So for example, you could have the same intelligent materials could be programmed and recycled again and again and kind of used in different products. I just wonder if you've had an eye on that when you've been designing some of these materials.
Yeah, definitely. Neil Gershenfeld and I think others have rightfully credited if you go in the forest, there's no waste in the forest. That everything is built up and destroyed and rebuilt up into something else. That, there's a perfect circular relationship there about the material parts that can build up and disassemble and build up and disassemble. And that's not the case in our human built world. So if we had the capability to have some fundamental material components that could be built up and disassembled, you could theoretically have no waste, that everything could be built up and disassembled and built up and disassembled. So, I'll put that out there as a kind of theoretical space that we're not there. There's lots of other things that I think are much more near term, like the granular jamming space where you can build and disassemble and there is no waste, or the metal printing where there's literally no waste. Everything we print, we then reprint again and again. So there are ones that today we have shown you can build, disassemble, and each time build it different. It doesn't have to be made the same thing. And there's not a deterioration in the same way that you often find, with plastics, for example, that may only be able to be recycled a few times. Knitting is another interesting one because it's made with continuous fibers, different than weaving. So there is the potential of, it's almost the dream of a single strand that makes a sweater that then goes back to a single strand that then makes your shoe, or, there are really interesting scenarios in that space. And I'm very much interested in that macro scale recyclability, not like the holy grail material that will solve all of our problems. May or may not be there. There's lots of brilliant researchers working in that space. We look at it from a macro scale perspective, like literally how are materials combined and recombined so that they can be reusable or useful and functional in many different ways. Because it could be that it's not about disassembly. It could be that you design something that has one functionality, but the functionality can morph and change over time. That's another version of getting rid of waste.
Absolutely. Druv and King Yang both asked kind of similar questions. So Druv says, how can we speed up the time it takes to form the final shape? Like if the geometry is really complex, it's going to take forever for the final form. And King Yang says, are there any inherent weaknesses of the self-assembly process, like time? I just wonder, obviously there must be some applications that are more suitable than others, depending on how time critical they are.
Yeah, and I get the sense that they're talking about the self-assembly category of it.
Yeah.
Because on a lot of the other categories, different materials have different properties and different speeds and activation energies. Like often moisture is a quite slow activation energy, whereas temperature or sunlight can be quite fast. And many of those things are transforming in seconds and reversible and things like that. But on the self-assembly side, it is, because it's a stochastic process, it's very, very different than our typical assembly. But what I'm really interested in is that traditional assembly is linear, in the sense that, like, if I want to build more of something, I either need to go faster myself, but at some point you hit a limit, or I have to hire more people or have more robots to do it. It's more people, more parts, or more robots, more parts. It doesn't scale non-linearly. But what's fascinating about self-assembly is that in order to get more of something, you can have more parts in the exact same chamber with the exact same pumps in the same environment. I can build one thing, or I can build 100 things spontaneously at the same time. So in that, and we've done a bunch of these experiments where, like, in that shaking jar, I had one thing. I can just have a shaking jar with 1,000 parts. And at the same time that I'll get one thing, I'll get 100 things, or, whatever it is. And so it's really interesting how it scales up and scales down. So you can make it faster by having many, many more parts. You can make it faster by really controlling the energy landscape. A lot of those are noisy, kind of down and dirty things where, like, I'm shaking. That's definitely not an efficient way, but if you have a tumbler that you can program exactly how it shakes, and so a lot of this often is done in chemistry, where you change the temperature, or you vibrate things or agitate things in very precise ways. You try to catalyze things by the environment, so you can kind of speed it up in that way. You can have kind of sequential processes, like one thing happens and then that kickstarts another thing to try to speed it up. But one other point I'll make is that this happens all the time, in a fairly fast way. I mean, look at humans are made in roughly 9 months. Plants grow very, very fast. There's many biological examples. Think about weather patterns. Think about traffic jams. There's many instances where self-assembly and self-organization happen in both biological, organic, and inorganic examples around us at huge scales, small scales. Some are super fast. Some happen on, like, geological time scales. Like, there's nothing fundamental that says self-assembly or self-organization can't happen spontaneously very, very fast, or be very, very slow, or be very large, or be very small. It's a fundamental phenomenon. It's a principle that we can tap into, but we have to design around the environment, the material parts, the energy source, in order to try to guide it. It's very different from how we manufacture today, although there are a lot of examples. Think about, like, cooking or baking or gardening, brewing beer, cheese. A lot of these phenomena, you don't have control over every single step of the way. You can control some of the ingredients, you can control some of the environment, but you have to collaborate with the material medium to collectively build something. And that's kind of where we're going. It's very different than, brick by brick or part by part with a robot. It's really a material collaboration. And through that, we're able to get on the cooking spectrum, things like, McDonald's and industrial production, all the way to nuanced chefs that never make two things the same. And, we're totally fine with cooking being, a self-organizing process, but we're not fine when a car is made that way. So there's a really interesting question mark there. Like, why are some things open to being bottom up and other things open to being top down?
That actually leads on to a question by Path that says, what kind of structural integrity can self-assembly structures offer? I'm just thinking when you mentioned a self-assembled car, I'm like, if we can't control every aspect of this process, and it's just, will it be safe?
Yeah.
So are there any concerns about that if you're not fully in control of the process, that therefore the safety of things you might produce might be compromised?
Yeah, well, again, maybe this is too theoretical of a response, but there's nothing fundamentally that says self-assembly is weak. Like trees and humans and bones, like think about how the structure of our bone changes based on the environment we're in, the behaviors we have. If you're in outer space versus on the ground, the structure of your bone adapts and morphs. Or if you're a runner versus if you've never ran a day in your life, or if you live at one altitude versus another. And our materials are incredibly capable in terms of adapting, and we're quite structurally sound, and trees and mountains and all sorts of things out there in the world are built from the bottom up and self-organized through forces in the environment. And so, yeah, you can have very weak things and you can have very strong things. There is a question on how do we achieve that? So that is a hurdle. Like, how do you achieve it in a sort of industrial setting? Like, I have some parts, I have an environment, whether that's like water or tumblers or temperature or whatever it is. And how do I get these parts to come together to make strong? If strong is the goal, like structural performance is the goal, how do I make the strongest possible structures self-organize? I'll give you another example where we had this aerial chamber, like a fan with particles floating around, like a lottery tumbler, for example. And they would connect, and then they would fall to the ground and disassemble, disconnect, and connect and disassemble, and over again, like a lottery tumbler. But eventually, a few of them connected, and they were very good at flying. They would just hover. And so a fitness criteria emerged, which was flying. And we didn't teach them how to fly. We actually didn't even realize that was going to happen. But they then started to fly, and they didn't break. And so to me, that points to a sort of evolutionary capability that we could set up an environment where structural performance is the fitness criteria, and design and functionality could be built where we could maybe find a structural solution that we never would have guessed that could be far greater potentially than we would have built, or at least similarly capable, but the materials built themselves. And so it's just about how do we design that is really the question of, is it possible? Yes, it's possible. Can we figure out how to get there is the bigger question.
And you've sort of hinted at the great advantage of this, which is that the self-assembling materials might assemble in a way that we didn't think of and produce a better solution that we'd, ordinarily used.
And lots of people look at evolution and it's not ideal, and there's many dead ends and there's many non-optimal solutions, but there are wild and weird solutions that humans probably would not have come up with. And they're based on very specific criteria with very specific environments, conditions that led to these solutions that are quite frankly fascinating. Look at, any Planet Earth or like documentary, there's weird things out there. Like, how did that evolve? And I'm very fascinated in promoting design as a bottom-up process. It may be performance driven, or it may be creativity or aesthetics driven, or many other things. But I'm very adamant that design solutions will emerge that humans or robots and machines likely would not have come up with if we're giving them the agency to do that.
So building off my quest for a magic jumper, Strazian asks, which of these innovations do you think is most likely to be commonplace within the next decade? Now, obviously, some of these technologies are already being used, but which of them that aren't currently on the market, particularly for consumers, I'm just thinking about my jumper again, do you think I'll be seeing in the shops, or it will be available to buy, or be in our homes or cars or wherever?
Yeah, and the first thing to say is that everything I've shown, or almost everything I've shown, is a collaboration with an industry partner. And you probably heard that throughout, cars and shoes and clothing and all that. We do collaborate a lot. And so although it sounds very sci-fi and far futures, and that is sort of our bread and butter, that we're a research lab, so our only goal is to continually invent what's next. But we do collaborate with all these industrial partners, so they do transition themselves to real world markets and products. Either our industry partners do it or we do it. We spin out companies to do this. But I think the most promising space is in the medical space. And it's frankly something that we're doing a little bit of, but is not our main thing. And I'm, brilliantly surprised that this emerged. I would not have guessed that. And I wish I would have predicted that. When we came out with the 4D printing work, that was the number one application that then boomed. There's lots and lots of researchers focusing on this. There's been surgery that implemented this in various places in the world. And the reason is because everyone's body is different. Surgery, for example, is really dangerous. It's really challenging. I'm going to cut you open, and inside I have no idea what I'm going to find. And it's going to be different than the previous person. So it's a really interesting challenge, design challenge, functional challenge. It's a harsh environment. No one wants to do surgery if they can. You don't really want to rely on like an individual's hand-eye coordination or even a robot doing this. So the dream is that if you can easily produce a material that has enough intelligence that you can deposit it in the body, solve a local problem, and adapt to the conditions, it's huge advantage over today. And we have things like stents, and in the medical space, like if you look at orthodontics, like braces, or you look at stents, it's one of the spaces where smart materials has been used for many, many decades, because it's such a challenging and customized scenario. Like everyone is different. It's so complicated and dangerous. So that's where you're seeing these huge advantages to smarter and smarter material systems, but they can't be like crazy expensive and complicated. People don't want that either. We have to be able to fabricate it quickly. And so that's where the promise of 4D printing is really making a huge change.
You mentioned working with various industrial partners. I know some of them were the US government. Are you working with NASA or ESA to research things like sending self-assembling probes to planets? Because presumably, if you could send something, like, because the communication is hard between us and probes, if something can be smart and assemble itself without us doing anything, presumably that would be quite a useful function. Yeah,
we don't have any research projects with them. I mean, we've talked to them and given presentations and applied for grants and connected with them sort of like through an adjacency, but not directly. And I totally agree with you. It is a crazy challenge to build in space, and there's very specific conditions with, sun and darkness and every 90 minutes and temperature changes and all sorts of things that make it very challenging for both humans and robots to build. And so therefore there's a huge advantage to using smarter material components. And there's a legacy of self-assembling systems and transformable materials in the space world. And so, there are people working on that, and we've connected with them, but we don't have any active research on that.
Shame. Well, I'll write to NASA and suggest they give you a call.
Yeah, if you want to connect us, rapidly.
It's a very, very quick specific question from Nick Whitehead, where he asks, are the STL files available for the print on stretch light grid designs and so forth? Like, how much of your work is open source in that way that people can just download the files to their own printers or whatever to use? Yeah,
so we're open as much as like any good academic would be open, in the sense that, we publish papers and we, publish our designs and tell you how we make it and what the materials are and what the forces are and that kind of stuff. But I wouldn't say that we're like open in terms of like open source, and that it's definitely not a main driver of our work. Not that we're against it, but it just doesn't tend to be like what we do. And I think most of that emerged because a lot of the designs, like the shape of the shoe, or I don't know, the code that we write to run this thing, or, even the machine that we build or the material composition, they're so specific and nuanced to the thing that we're trying that it tends to be like these tools we find not particularly useful to just like hand over. There's so much built up intuition, and, most academics don't typically want to talk about that, because we're supposed to have, purely repeatable research, and we try to do our best to do that and write it up. But we're also designers and artists and creatives we're both, we're engineers, scientists, and designers and artists. And, one thing that most people often don't talk about is the intuition that's built up. When we work on a self-assembly project or 4D printing project or programmable materials project, there's months and sometimes even years of failures, of tests, of iterations, of empirical knowledge built up in order to achieve these successes. And we then end up in solutions that are very, very specific to the things that we're trying to use, but oftentimes not just like widely generally applicable, because there's so much of this, tacit knowledge built up. And so anyway, that has led to us being like, our goal is often not open source. Our goal is to go from impossible to possible. And that's super difficult most of the time. It's just like, to get it to work is like the biggest challenge for us. And so then we get it to work and demonstrate, that it's possible. And then the other thing is that we often work with industry, and some industries are more open to being open, but often they're not particularly excited about being super open. And so, we do a lot of things that then they're interested in commercializing, and, then they want to develop it. But anyway, we do, as any good academic does, we do publish all of our results and all the details of how we do it.
Fantastic. A couple more questions here. So one interesting idea that Bradley asked about, which is the idea of self-assembly hierarchies that could be required to produce such materials. So you could have, for example, some small nanoscale things that produce a material that then builds a thing that then a series, do you see what I mean? And sort of the self-assembly would kind of work on a number of levels. Is that possible?
Yeah, and that's how biology and humans are built.
Yeah, it's true.
You have different levels of self-assembly. At every level, it's self-assembly, and they're built on the previous levels structures that are built. All the way from like DNA and proteins to biomolecular structures to cells and all these other things. So for sure that is possible to do. And we've done a couple things around that, like the one in the shaking jar. We did a project where you had units that were sort of like Siamese twin ones, like back-to-back units, so that when one would build, it would then build another one on its back, and then those could build like dodecahedrons on top of those. So there are some things there. I think the one that's more interesting is like how you can have hierarchies, but also timed sequences. So like there's some activation that promotes the self-assembly. There's another activation that promotes disassembly. There's another activation that promotes some transformation. Like I'm really interested in those, how you can have different sequences of behavior of assembly, transformation, disassembly.
Fascinating. Just on sort of the future of your work, would you say that the technologies, this is another question from Bradley actually, are the technologies limited more by material science, would you say, or is it sort of computational design, or what would you say would be the thing that you would wish for? Stronger materials, better materials, better computers, better knitting machines? What would you say is the thing that's limiting at the moment?
All of the above, maybe? It's a fascinating question. And there's also this weird shift where, previously, or like historically, we could make things that we didn't know how to design in terms of like software computation. So there was so much skill and embedded knowledge in craftspeople that it would be very, very challenging to try to replicate that. Then you went to a space where computationally you could design things that you couldn't fabricate. Then you went to a space where the fabrication processes are so sophisticated in knitting, for example, or multi-material printing, that the computational tools can't keep up, that we can't actually even design for those machines today. There's a lot of things that machines can do that we don't even have design tools to tap into, which is really, really interesting. And so we kind of go into these like weird reversals where one is like really far ahead and then the other one goes up, and you go back and forth. I would say right now, yes, we would love different material properties, but I don't think that the material science is the fundamental problem. I'm biased because our lab, we think about it as a macro scale materials space where it's not about the holy grail material like I've talked about before, but that we can do almost anything we want to do with all the abundant materials. We have tons and tons of materials around us that we can utilize in unusual, awesome ways that we aren't doing. So that's like, lifetimes worth of work in there. It's not that we need this like one specific material. I actually think it's computation. Again, and yes, we have powerful computational tools and capacity. Yes, we have simulation, but almost every one of our projects is so complicated to simulate. And many examples, we've spent years working on sophisticated simulation tools to try to be able to do what we could already do. And we then, in some cases, were successful, in other cases weren't successful. But even in the case we were successful, we would change one thing about it and the whole simulation tool is totally useless again. And now you got to spend a whole another year. And so, for many years now, we have not been that successful in building simulation tools. And there are experts out there, and we try to collaborate with them. And there's companies out there, and we've done all of that. We've done our due diligence, and we do it ourselves. But frankly, we're much faster at designing and fabricating than we are in simulating any of these things. 4D printing, textile, like almost no one can tell you if you have a sweater and you stretch a hole in the front of your sweater, what happens to the back? How do the forces translate in the back? Like almost no one can simulate that weird phenomenon. Or granular jamming. Lots of people can simulate spheres in a digital world. Almost no one can simulate rocks, every single rock being different in a structure that's formula tall. Almost no one can simulate what's going to happen there. We build it and we load test it and we see what's possible. Same thing with the self-organizing sand. You could simulate some small idealized sand particles. No one's really simulating how islands are formed in the way that we're talking about. Like there's really huge gaps there in terms of simulation. So the dream of like, oh, we just simulate everything and then we build it is totally not true. Oftentimes we build it and then we scramble to try to get anywhere close to being able to simulate something that's remotely useful in terms of our design process. What we're shifting towards now is, I think, a smarter model based on machine learning and AI and computer vision and stuff, which is basically build dynamic systems and then train your computational model on dynamic systems in order to build reverse engineer simulation tools based on physics, not trying to mimic physics.
So it's almost
that's
like
kind of the direction.
Like a sort of empirical simulation that you get at the end where you've just built it.
We would do it old school style where we would just make 100 things, each one slightly different, test it, and put that into some database, and then basically build a simulation off of like pure physical data. That's how we would do it before. I think it's going to be much better, in the coming years because of machine learning.
So we've got a few minutes left. I'll just throw a few more questions at you before we leave. One's a bit more of a philosophical question where S. McNeil said, are you sort of creating a different type of von Neumann machine, a universal constructor? And Steve asks, has there any thought gone into the unintended consequences of this type of work manufacture? Basically, I think what we all want to know is, are you going to create an army of self-replicating robots that's going to destroy the world?
Yeah, exactly. Yeah, to the first question, actually, my master's thesis at MIT was called Logic Matter. And it was demonstrating that we can have digital logic in the computational sense, like a NAND gate, like and, or, nor, XOR, a functional NAND gate, which you can build any other, gate and circuit and computational tool out of a NAND gate. You can do that purely with geometry. That it's not about silicon and transistors. It's not about material properties, even. It's about geometry in that example. And so in some ways we are trying to build computational tools out of physical things, not necessarily to compete, because I don't think that the goal is to try to be faster or have greater capacity than silicon or transistors or quantum computing, or they're doing pretty good at speed and capacity these days. But there's a lot of other things, like I was saying before, that materials and geometry are much more adaptable. They're much more in tune to the environment. They can assemble, disassemble, reverse, weird things that typical computers can't do. And so, we're interested in building computational tools through materials because of that. And then can they take over? Will they take over? This is often a question that we get. So the short answer is like, yes, we're definitely tuned into that. And we try to build in tests and safeguards, and like in the Maldives, we try to do analysis in like what marine life has been there, what impact are we having, and try to study that to make sure that we're as responsible as possible as these scale. But I think that there's also hidden underneath that question, like there's an inherent fear of newness, like of new technology, and you can go to like any new technology, whether they're hyped and feared ones like synthetic biology, CRISPR, GMOs, lots of debates around that kind of stuff, all the way to like the computer, the cinema, the whatever, the car, the whatever it is, and there's always a fear of like the new technology will take over and destroy the world, which luckily has not happened. It doesn't necessarily mean that that's not a legitimate fear, but I guess our relationship is, we're academics, and so the goal in a research in our lab is, as I've been saying, to push the boundaries of what's possible, to ask the questions and to continue to invent and go from impossible to possible. Like that's our only goal. And we need to have a really strong relationship between the policyholders, the people that are making policies and regulations around new technologies and how they get implemented, and the stakeholders, whether that's the industry partners or the everyday people that are going to be using these things, taking advantage of them, or being taken advantage of. You have to have a really strong relationship between those. And the problem lies when those three parties don't talk to one another. When technology advances so fast, whether that's, synthetic biology and CRISPR, and then, it's used in China or some other country that doesn't have exactly the same policies or regulations, and it goes way too far beyond what should have happened, as we saw recently in the case of that, or in, Bitcoin or many other examples where policy can't catch up because it's so fast, or someone uses it in the wrong way, industry players, stakeholders, whatever. So, it needs this really strong relationship. I don't have the holy grail solution of how do you create that dialogue, but I think it is important that we need to keep pushing the boundaries of what's possible while staying in communication with the other parties in order to make sure that, there aren't unintended consequences. Luckily, our things don't go out of control in the lab, and we're talking about, tens of parts, and it takes lots of work to make these things even feasible. But there's a lot of other questions on how these things translate when the same stuff that we're doing happens on a biological scale. It's a lot easier to make millions of things and a lot easier for it to have, damaging effects in society.
So we're almost out of time, but I'll sneak in a final question. So Kinyang asks, can a degree in physics lead to research into this? And somebody else asked, were you kind of inspired by science fiction and other things in your research? So if you could just say a little bit about how you ended up in this field and what you would advise, a teenager watching who's suddenly seen all this amazing research we're doing and has gone, I want to do that. What advice would you give them?
I wasn't really that into sci-fi as a kid, to be honest. But if you look at the movie Big Hero 6, they actually
somebody mentioned that in the chat. Yeah.
If you look at that, in the credits, they were at the Center for Bits and Atoms at the same time that I was there, and that robot that I built was called the Macrobot, and I think the robots in the movie are called the Microbot. And they have soft robotic, inflatable, morphable things. Like a lot of the technologies were built based on some of the things I'm talking about that Neil's lab, the Center for Bits and Atoms, was developing, and various others as well.
Amazing.
So a lot of science fiction was based on that kind of stuff. And that happens all the time. They're kind of bouncing back and forth. And scientists often are riffing off of that. There's a joke that if you want to get DARPA funding, you need to go to a cartoon or science fiction and say the Terminator or invisibility cloaking or the Replicator, Star Trek Replicator, and those will be the funded. So there's kind of a joke that they go back and forth. And movies are often ripping off of latest technologies as well. And I think that's a kind of healthy inspiration dance. But it, frankly, it wasn't the case for me. I wasn't huge into sci-fi as a kid. I was really into sports, and I was really into art. I have a bunch of artists in my family, an architect grandfather, and I wanted to be an artist or an architect, and I was interested in that, pure creativity space. And then I got interested in computer science through that because I started getting more and more into software and realizing code was like sketching. Once I became really good at writing code, I could sketch through code. I could think through code. I was so fat, and I was really interested in the messy code, the code that made mistakes, the weird code, the code that whoa, why did it do that? That's crazy. Go after that. The same way when you're sketching and you're just oh, that's a good idea. Let's do that. It was a collaboration with the medium, and it wasn't oh, I can make the most efficient code or the most precise, optimal. I was more into the messy, sketchy code. But I think you can get into this from almost any angle, from a physics angle, a biology angle, material science angle, astronomy angle. You can get into this research because it's so cross-disciplinary. It's left brain, right brain, technical and creative, and there's so many ways to get into it now.
Fascinating. Well, that's a really, really positive note to end on. Thank you so much. Just before you go, I just want to say thank you so much to all of you in the chat for all your amazing questions. I barely scratched the surface of some of them, but yeah, there were some really great comments in there. So thank you all for your contributions. Just a reminder, anyone in the world can join as a member of the Royal Institution. You don't have to be a scientist. You don't have to be nominated. You don't have to be anything like that. You just need to like science, like what we do, and want to support us. So do check that out on rigb.org. Just before you go, Skylar, is there anything else you'd like to plug? Where can people find you on the internet? What's the title of your book and all that kind of thing?
Yep. So Things Fall Together, A Guide to the New Materials Revolution is the title of the book, coming out June 15th, I believe. And then you can look us up, the selfassembly.mit.edu, and you can find us on all the social media handles.
Fantastic. Well, thank you again for just an absolutely fascinating evening. It's completely flown by. And thank you all for joining us. And so just time for me to say good night to you all. Good night.